Let's see how the chain rule is helpful when we're dealing with bell curves like you would see in a probability class or maybe statistics. You might have also heard them called normal curves or Gaussian curves. Let's start with something that's not a bell curve but is a good lead up. What's the derivative of e to the negative x? We've actually done this on a previous video, so pause the video and go ahead and do it real quick. So I'd say that's e to the negative x times negative x prime. And I'm not just copying the e to the negative x. What I'm using here is the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I'll say here, we're not just copying. If this wasn't e to the x, if it was something else, we would have to take the derivative of the outside function. It's only because it's e to the negative e to the something that we're appearing to copy. So we're saying derivative of e to the stuff is e to the stuff times stuff prime. And then what's the derivative of e to the, what's the derivative of negative x? It's just negative 1. So you can write that as negative e to the negative x. And we graphed this before. Here's our original function. And here's our f prime. And you can check that that satisfies the right derivative relationship. Now let's try something like a bell curve. So e to the negative x squared, derivative of that. Let me just graph that real quick. We get a bell curve like that. That's our function. So go ahead and write the derivative. Okay, welcome back from pausing it. So derivative of e to the stuff is e to the stuff times the derivative of the stuff. So e to the negative x squared. Derivative of negative x squared is negative 2x. Notice you have to have that parenthesis there or a times. You can't just leave it as a subtraction. And you can move it around. You don't really have to. So let's graph. Here's our bell curve. And then if you go graph that in Desmos, what do you see? Zero slope right there, negative slopes over here that get fairly steep but then get shallow again. So it actually does that. And over here, positive slopes that start fairly shallow, then get steep, but then go back to 0. So it's actually doing something like that. So doing good there. Now we throw a wrinkle in it, and I'm throwing this in because it actually happens in statistics, more in probability maybe. E to the negative x squared over 2. So note that that's not e to the negative x to the 2 divided by 2. So the over 2 is multiplying the x squared, it's dividing the x squared. You could write this as e to the negative 0.5 x squared. Maybe that's more clear. So what's the derivative there? It's going to be very similar to this. So we'll have e to the negative x squared over 2 times negative x squared over 2 derivative. E to the negative x squared over 2. Derivative of that is negative. The 2 comes down in front of the x over 2. You could cancel these 2's if you want to. In some sense, that's kind of why the 2 is there in the denominator. It's kind of waiting to capture the 2 that comes down. That's not quite true. The bell curve really, the standard bell curve really does have a divide by 2 here, and it's not exactly just to make a cancellation there, but we'll end up writing it like that anyway. And then how does the picture look here? It's the same basic picture, but because we're dividing x squared by 2, we're basically making it smaller all the time. So if x was 1 before, I used to get e to the negative 1. Now I'm getting e to the negative half, which isn't as small. So I'm getting something that's a little wider. And then we get the same, so it's not just a little wider, it's a factor of 2 wider. Or square root of 2? You got to think about that. Okay, but same basic shape. Okay, now life gets really complicated. Let's try, this gets really tricky, e to the minus x minus mu squared divided by 2 sigma squared. Bell curves can describe a histogram, and histograms often have a mean, which we call mu, and a standard deviation, which we call sigma. So instead of just dividing by 2, now we're dividing by 2 times sigma squared. And in the numerator, inside the exponent, we're subtracting mu before we square stuff. So what's the derivative? So the mu moves things left and right. The sigma changes the width of things. That's why we have these, because not every bell curve has a mean of 0 and a standard deviation of 1 like this one does. All right, so the derivative of e to the stuff is e to the stuff. So we copy all that stuff times the derivative of that inside stuff, negative x minus mu squared divided by 2 sigma squared derivative. Phew. Okay, I can just copy that part, just like I did above. And then what do I do with all this? Do I need the quotient rule because I'm dividing here? Think about that. Well, sigma is meant to be constant with respect to x. It's just the standard deviation of the bell curve. So the denominator is a constant here, so I do not need the quotient rule. I can actually bring it all the way up front if I want to. I can multiply by 1 over 2 sigma squared there, and then I've got just the derivative of negative x minus mu squared. The negative I can just keep as a negative 1. And then what's the derivative of x minus mu squared? That's 2x minus mu to the 1. That's to the 1. But then, since I'm squaring something and there's something inside that, I have to multiply by x minus mu prime. Now fortunately, x minus mu prime is fairly simple. It's just x minus a constant. So we just get here 1 minus 0. So that term actually ends up just kind of being ignorable. It's just a 1. But it just to be thorough with using the chain rule, we should make sure it's there. Oh, I forgot I should do a brief Greek letter introduction. So mu is this, and you write it mu if you don't have a Greek keyboard handy. This letter is sigma, and some people get that confused with theta. Theta has a line horizontally through the middle. All right. Oh, and we'll write that this is often the mean of the bell curve. Sigma is often the standard deviation of the bell curve. Standard deviation of the bell curve. And theta is really not used with bell curves. In some of the upper level stat courses, you would use theta. Let's show all this stuff in Desmos. All right, I've got my bell curve formula typed here with M for mu because I couldn't find mu on my keyboard, and S for sigma because I couldn't find sigma on my keyboard. In stats, we actually make a difference between S and sigma, so I feel a little weird doing this, but that's okay. Here's the derivative formula we just got on paper, and here's f prime the way Desmos computes it, and it looks like we're doing a good job there. Let's give ourselves some more space here. What happens if I change mu? If I drag it, so changing mu to be 1 makes the bell curve peak at 1. Changing it to be 1.4 makes the bell curve peak at 1.4. What happens if I change S? Making S larger makes the bell curve wider, increases the standard deviation. Making S smaller makes the bell curve skinnier, and seems to be making the derivative taller, because making the bell curve skinnier makes it increase quicker to hit its maximum there at 1. there's another wrinkle to the bell curve story, that usually we have a 1 over root 2 pi sigma squared out front that we've skipped here, but that's just a constant. All right, we can decrease sigma even more, get a very peaked bell curve, and get a really tall derivative. So that's fun with bell curves and the chain rule.